This is the first problem for PA9, so D5.53. In this particular problem, we have this circuit here on the left. We have a PMOS transistor because of the arrow. So the arrow here, right, it gives us this, because of the symbol, it gives us the information that we have a PMOS transistor. And given that the threshold voltage is minus 1.5 volts and the device transconductance is 4 milliamperes per square volts, and we are ignoring the channel modulation effect, so lambda equals 4, we need to design this circuit. So choose our G1, G2, and source and drain resistors, so that we have first a gate voltage of 6 volts, a drain voltage of 0.5 milliamps, and a drain current of 0.5 milliamps, and a drain voltage of 5 volts. And this IVD here is that the current that's flowing through the voltage divider here at the gate, so this current here is 1 microamp. Okay, and we know that because it's one of the parameters from the problem, and that because of the behavior of the MOSFET, right, this current IG is equals to 0, because ideally there is no current flowing from the gate to the drain. Okay, so we just need to define those parameters here, right? So if we start with RG1 and RG2, basically we know that the current at the voltage divider is 1 microampere, and that the voltage at the gate should be 6 volts. Those are the parameters that we have to design RG1 and RG2. Now if we look at the circuit, we know that the voltage at the gate, so VG here, is actually the voltage across RG2, right? And basically the voltage across RG2 can be calculated as VG equals to 10 volts times RG2 divided by RG1 plus RG2. Okay, so basically that's the 6 volts that we want to have, right? Now we know that this VG here is also equals to that IVD times RG2, and because we know that the gate voltage at the gate should be equals to 6, and this one here should be kept at 1 microampere, this gives us an equation for RG2. So in this case, RG2 is equals to 6 volts divided by 1 microampere, and that's 6 mega ohms. Okay, now for RG1, we basically apply this same, we use this equation up here, right? Because we know this one, now we know RG2. Okay, so we define RG1. And if we isolate RG1 in that equation, RG1 is equals to 10 divided by VG times RG2 minus RG2. This gives us RG1 equals to 10 divided by 6 times 6 mega ohms minus 6 mega ohms, and this gives us RG1 equals to 4 mega ohms. Okay, this is just because we have a voltage divider here, right? So there's a current flowing here, right? And there's no current flowing here because the current at the gate is equals to 0. So now we have designed those two resistors. Okay, so we still need to find out the value of RD and RS. So for RD, okay, because we know the current that's flowing here, right? The current that's flowing through the drain is 0.5 milliamps. And we know that we want a voltage at the drain terminal equals to 5 volts. Basically, if we apply Ohm's law here, so find out the voltage across this RD, we know that RD is equals to those VD minus 0 volts divided by ID, right? And this gives us 5 volts divided by 0.5 milliamps. RD in this case is 10k ohm. Now to calculate RS, we need to use the equation for the current ID that depends on the process transconductance or the device transconductance and the overdrive voltage, right? So we know that the equation for current ID or IS in our case, because it's just the same current, right? So ID is equals to 1/2 the device transconductance times the magnitude of the overdrive voltage squared. And this is assuming that the device is operating in the saturation region. Okay, so for saturation region, one of the conditions is that VDG should be less than the magnitude of the threshold voltage of the PMOS. And from this condition here, basically we know that VD minus VG should be less than the magnitude of the threshold voltage, so it's the magnitude of minus 1.5. This one here we know that is 5 because that's what we want. Minus 6, that's the voltage at the gate we also want. That should be less than 1.5. And indeed it is, right? Minus 1 is less than 1.5. So based on this, based on the conditions that the problem is giving to us for VD and VG, we know that it's working in the saturation region, so we can use this equation here, right? So from this equation here, we can actually determine the overdrive voltage, right? Because if you remember, the overdrive voltage is equals to VGS, so the magnitude of the overdrive voltage is equals to VSG minus the magnitude of the threshold voltage. So if we define the overdrive voltage, we can define Vs in here because we know Vg. So from this equation, right, we can isolate V overdrive. So V overdrive is the square root of 2 times ID divided by the device transconductance. So this gives us an overdrive voltage of 2 times square root of 2 times 0.5 milliamps divided by 4 milliamps per square voltage. This gives us a V overdrive of 0.5 volts. And this V overdrive we can use to calculate the voltage at the source of this voltage here, right? Vs. Because we know that this overdrive voltage, so the equation that I had before, let me write here. So Vs minus Vg should be equals to the magnitude of the overdrive voltage plus the threshold, the magnitude of the threshold voltage. And this gives us Vs equals to the overdrive voltage, so 0.5 5 plus so that's let me just write here Vs minus Vg equals to 0.5 plus 1.5, and that's equals to 2. And because we know the value of Vg, right, is 6, so we can isolate Vs here, and Vs is equals to, so it goes to the other side, positive, so it's 2 plus 6, which gives us 8 volts. So that's the value of Vs. And now with the value of Vs, we can apply Ohm's law here again, right, across Rs. So we know that Rs is equals to that 10 minus Vs, 8, divided by Id, which is 2 divided by 0.5 milliamps, and that's 4k ohms. And that's the final answer. So we got the values of the resistors here, Rg1, so Rg1 is 6 mega ohms. Sorry, it's not 6, it's 4 mega ohms. Rg2 is 6 mega ohms. Rs is 4k, and Rd is 10k.